So now we're going to write the stress-strain relationships. That is the relationship between the stress and the strain, or the deformation tensor B or C, or anything that links the deformation to the forces. And once you have that link, then you can write down the equations of equilibrium and solve them, and you'll find the shape, the forces, whatever it is you're looking for. You know, depends on your starting point. Maybe you prescribe this formation, then you find the forces that it requires, or vice versa. You prescribe a force, and you find the resulting deformation. Okay, so I'm just going to talk now about incompressible materials, because, like I said, many soft materials are incompressible. It means they do not change their volume. You can deform them. You know, think of jelly or rubber. You can stretch them. You can contract them, but you cannot compress them. That would mean that if you had like a sphere of rubber and you were applying hydrostatic pressure, you were putting them in a in a room where the pressure was going up. Well, the sphere will keep its shape and radius. Whereas if it was a compressible material, think of a sponge, for instance, or something of foamy, then it will shrink, right? It will just contract and compress itself. So most materials, or many materials, are incompressible. Rubber or materials that have a high fluid content, like gels or biological solids. So let's just write this, incompressible. And we've come across that notion earlier, elastic solids. Oh, almost. Oh. We come across that notion earlier when we were talking about volume changes, right? So an incompressible material is one for which only isochoric deformations are allowed to take place, if you want. And isochoric, we've come across that word before. Iso means same, and choric, it's reference to the volume, right? It means no volume change. And that means that J, which is the determinant of F, must be 1 at all times, everywhere. That is the condition, so that there's no volume change anywhere in the solid at any time. That's the local condition, and you have to enforce it. You have to make sure that it's respected. Okay, so what does that mean from the point of view of the relationship between the stress and the strain? It has a funny consequence. I'm just going to talk back about the work. Consider the work done for nominal stress tensor. So S and small change in the deformation gradient. If you remember, I think I showed that. Actually, we had gone as far as writing it as a differential. Did I call it W? I can't remember what I called it. Yeah, I think so. We found that there was trace of STF for a compressible material, right? And now, what if the material is incompressible? Would that have any bearing on the work done? It does. It's quite quirky. You will find that this work is the same. It is the same as the work done for this quantity of stress. Pf minus 1, where P is an arbitrary scalar. And that seems strange, but it's true. And I'll just show you the proof now. If I compute the work done by this stress, S df minus 1 df, so that's the stress of a tensor, the tensor in the brackets, multiplied by another tensor, so it's a product of tensors. The first tensor is the sum of two tensors, so the product of the sum of two tensors is the sum of the two products. So I can write like this: SDF P looks like P is just a scalar, so I can take it out of the trace. So if this was to be the same as what I have above, then this quantity here, P trace of F minus 1 df, should be 0. Is that true? Well, recall that very nice identity is Jacobi's identity. So I think that's in the tutorial sheet. I forgot to check, but presumably Harold has done it with you. But if f was a function of a variable, in fact, we use that formula to derive the derivative of j of I3 with respect to f. Yes, Fij. If f was a tensor that depended on any variable tau, say, or x, or whatever you want to call it, you will find that this applies f minus 1 df d tau. For any theta. So in general, we can write this f minus 1 df, and now so that I can see that the right hand side is going to give me that quantity, depth of F, that's J, but that's 1 for incompressible materials. And so I just have a variation of determinant of F. The determinant of F is 1, so the variation is 0. And so I've proven what I'd written earlier. The work done by the stress tensor S is the same as the work done by the tensor S plus PF minus 1. So that's a bit mind-blowing. It's not mathematically, you could see what it means. This here, this condition that I'm imposing, it's a constraint, right? I'm forcing the fields to be such that only those that satisfy this constraint are allowed. And so when you impose a constraint, you might have seen this in calculus, then you are restricting yourself to a subspace of all the solutions. And then we should look at P here as that arbitrary scalar as a Lagrange multiplier. So I don't want to go into those details. It's just a bit too advanced mathematically. But we could just see that whether I use S or if I use S plus PF minus 1, where P is any scalar, I will get the same work. And so there will be no change. It will be the same solution, right? The principle of work will yield the same equations, and whether you use S or S plus PF minus 1, you will have the same result. And so we must include this in our description of the stress-strain relationship. We must include that arbitrariness. All right, so stress-strain relations, for incompressible material. We're going to deduce it. Oh yeah, we're going to deduce it for the Cauchy stress, right? So S plus P. And then means sigma and work. Why did I write this? Oh, I don't really like it anymore. Because if you recall, sigma is J minus 1 Fs. Here J is 1, and then if I add the term Pf minus 1, then that's the same as adding the term Pf F minus 1, which is the identity to the Cauchy stress. No. Stress. Cauchy stress. So if I look at the, so I'll just write it down. If I look at the stress-strain relations, I can say now we may add Pi, and it won't make any difference to my equations. My stress-strain relations, they read like this: 2J PWD I3I. This is what, okay, I'm taking shortcuts now. If you have the index for the W, it means the derivative with respect to I1 or I2 or I3. Yeah, this is the expression that Giuseppe established. But here, J is 1, incompressible, and W, which in general is a function of 3 invariants of 3 scalars, I1, I2, I3. Here, I3, that's J squared, I3 is 1, right? So I3 is not going to merge, and so W is a function of 2 invariants only, I1, I2 only. And my first quantity here is going to be 0. Here equals 0. Since W does not vary with I3. And then here I'm going to have J replaced by 1. In the end, I end up with this expression. Oh, sorry. Sigma equals minus pi plus 2 W1 plus IW2B minus 2 W2P squared. Where P is arbitrary. So that's a bit of a problem. What does that mean? It's arbitrary. It means it could be anything. We have to try to get rid of it one way or another. Eliminate it or find it using, boundary conditions or equations of equilibrium. Must be found, eliminated. So it seems all a bit mysterious, but I'll show you later how it works in the next lecture. Boundary conditions. Equations. Okay. And just to complete the picture, remember we can express b squared by using the Cayley-Hamilton theorem. We can express b squared in terms of all the powers of b. So that's what we're going to do here, just to have another expression in case we don't want to compute b squared. We can use Cayley-Hamilton theorem. Which is like this. It just says that the tensor satisfies its own characteristic equation. Now, I have a question. Let me see. Oh, I missed a lot of questions. Sorry. Why can d of tau be cancelled inside the trace? Oh, so I have to go back. Sorry about that. Oh yeah, so I didn't cancel it. I just said this here. This expression is valid whatever tau is, whatever F depends on whatever field you want to differentiate the determinant of F with respect to, you will always have this expression here. And so it means that this is true as well. The total variation satisfies this equality. Yeah, I'm sorry, it's not obvious. I can't think of any other way to explain it. Right? If I write the second one, I can deduce the first one. But if I can write the first one for any tau, any field, then I can deduce the second one. They're both equivalent. The total variation of F with respect to any field will satisfy this, of F and of its determinant. And then another question, are I1 and I2 constants as well? Right, so I1 and I2 are the principal invariants of the deformation, right? So you have a deformation, and then I1 is going to be the trace of B, and I2 is going, or C, they're the same actually, and I2 is going to be the second invariance. And you can express them in terms of the lambda, the principal stretches. For instance, I1 is going to be lambda 1 squared plus lambda 2 squared plus lambda 2 squared. And it's true that if the lambdas are constant, if I do what's called homogeneous deformation, then I1 and I2 are going to be constants. But it doesn't mean that the derivative is 0. Yeah, how to explain that? Yeah, if I have, like, say, f of x is x, and I compute that at a given constant value, if I'd say x is 3, okay, I should put 3x. If I say x is 1, for instance, then I know f of 1 is 3. That's a constant. But the derivative is 3. So the derivative at 1 is 3. It's not 0. Do you see what I mean? First you must differentiate, then you must take I1 equals a constant, so I2 is equal to constant, and see what happens. Don't know if I explained it well. These are hard concepts, all right. Don't worry too much. We'll do examples and you'll see how it works. Can you get df from from f? Yeah, if you have f, you can then take the full variation, right? If f is a function of, right? If f is given to you, if you're told that f is f of x1, x2, then you could say df is going to be df dx1 dx1. That's the total variation. Again, I hope I've answered that question. Good questions, hard answers. Well, hard to explain in such an abstract way. I should think of, so if f is homogeneous, then df is 0. And then is the work 0? Again, it's the same point as I was making earlier. First, you have to consider that the work is found by the variations and so on and so forth, and then you take the function to be the deformation to be homogeneous, and you plug that into the end. right? Just like I said, first you have to differentiate f of x equals 3x. You find 3, and then you can ask yourself, what's the value when x is 1, when x is a constant? You must first do the variation and then apply your deformation. Yeah? I must think of better ways to explain this. Oh, geez, only 10 minutes left. Okay. Here, I3 is going to be 1, so I just deleted it. And if I multiply across by b minus 1 times this, I'm going to get b squared minus I1b, I2 identity equals 0. And so that tells me that, yeah, in my expression above, I can see that I have sigma minus pi I to W1b, and then I can see I have an expression with W2 plus 2W2 times I1b minus b squared. Am I right? Yeah. I just factorized W2. And then I1b minus b squared, I find it for my line just above. As I2i minus b1. And so I can express the stress in terms of b and b minus 1 instead of b and b squared. Sigma is going to be, oh, and I can see I have a term in I, then I have a term in b, and then I have a term in b minus 1. And then this here, I'm going to call it p bar. And p bar is arbitrary. Why? Because p bar is equal to p minus 2I2W2, but p is arbitrary. P can be anything. And so that quantity p, that can be anything minus something, it's still anything, right? Bar is just as arbitrary as p minus 2I2W2 because p is arbitrary. Sigma equals minus p bar I W2p minus 1 where p bar is arbitrary. So that's a lot to take in. In the end, what matters are those two expressions. The stress-strain relation is very similar to the one when in the compressible case, right? It's the relationship between the Cauchy stress and the tensor B, either B and B squared or B and B minus 1. The one difference now is that there's only derivatives of W with respect to I1 and I2 that are involved because now I3 is fixed. There's no dependence of W on I3. And the other difference is that there's this arbitrary scalar that has been creeping into our equations because of that remark I made earlier. It doesn't matter whether you use S or S plus P F minus 1, or it doesn't matter whether you use sigma or sigma plus Pi, that will result in the same equations and solving the same problem. So you must account for this arbitrariness by adding that term wherever you can. And this is what I've done here in the first line of that page. I just say that sigma, which was the right-hand side for compressible material, can now be replaced by sigma plus pi. Then the right-hand side, I specialize that to the incompressible case. I2 is a constant, and so on and so forth. And then I end up with this nice relationship here, where p is arbitrary, or this one here, where p bar is arbitrary. And we are carrying this p or p bar. It seems to cause problems, but in the end you will see that it's easy to get rid of it, to eliminate it. Okay. So I just so that if you remember, there was another way of representing W. If you see W as a function of the stretches, then the principal stresses, and Giuseppe must have given you the expression, are sigma I. So in our case, it's just going to be this, lambda I dW d lambda I. And the lambda 1, lambda 2, lambda 3, they are linked. That's such that lambda 1 times lambda 2 times lambda 3 is 1. That's because if you calculate the determinant of f, you will find that it's lambda 1, lambda 2, lambda 3. I have another question. Can you comment on the physical meaning of the P parameter? P bar is not the full pressure, right? It's true, it's not the pressure, right? The full pressure is equal, as you say, to 1/3 of trace of sigma. So P or P bar, they are in front of I, so they are called spherical contribution. They are, you know, pressure terms. Some people say it's pressure, but that's abusive. It's the pressure. It's not the pressure. The pressure is 1/3 of trace of sigma. And so they are pressure-like terms if you want. You will have to call the pressure something else. I don't know, P0 or P tilde. So they have the aspects of a pressure if you want, but it's still an arbitrary field for the moment. I'll show you how it works in the next session. So here's the expression when W is a function expressed as a function of lambda 1, lambda 2, lambda 3. That's easy to prove. I won't go into the details because I only have a couple of minutes left. What I'll do now is I'll introduce some examples of W. Right, and this is it. Really, we've now arrived at the end of the whole journey. Remember, we had to describe deformation, stresses, how stresses and deformations linked. They are linked to those relations here in general. But now, for a given material, you have a given W, and so I'm going to give you a W. You're going to be able to tell me, oh, well, the stress should be related in that way to B or to whatever measure of strain you're choosing. And if you look in the literature, there are a lot of W's. Some people say this W is for rubber, this one is for soft material, for soft tissues, and so on and so forth. Some are popular, some come as in a fashion, and then they come out of fashion. Some are established, and you can find them in all the books and all the software, and so on and so forth. Okay, so the most basic one is the so-called neo-Hookean material or model. And it has an interesting history. If you were to do statistical mechanics, so I don't think you study statistical mechanics in physics at NUI, but if you were to do that and look at rubber as made up of long chains of polymers and so on and so forth, and do statistical analysis, you will end up with this W. And it reads like this, mu0/2 R1 minus 3. So very important historically, very popular for mathematicians because it's a very simple model, right? If I put that W just above there, I can see that the W2 is going to be 0, and I'm going to have, I can write it here, right? I'm using that frame formula. It's going to give me sigma equals minus P bar, or P, I can call it P, it doesn't matter, plus 2P. Very simple relationship between sigma and B. So popular with statistical mechanics or mechanicians, and then popular with applied mathematicians because it's very simple and you can actually find solutions, you can do analytical progress. Now, is it close to reality? I'll show you next time that it's not, right? There are no material that actually behaves in that way. But I still need to introduce it. Another one is the so-called Mooney-Rivlin material. Rivlin was the advisor of my, and it reads like this. Ah, question? No? C1 R1 minus 3. So I should say where mu is a constant plus C2 a positive constant. So the Mooney-Rivlin material is a bit more sophisticated because it has two constants now, and it counts for the first invariant and the second invariant, right? It's going to give you, if I was to plug this into this expression here, would be easy, right? I will have the derivative of W respect to I1 is going to be C2. So here is a good example, right? If I do derivative of W respect to I1, that's going to be C2. Even if I1 is constant, even if it doesn't vary, the derivative is not 0. So I'm going to end up with minus PI plus C1B minus 2 C2B minus 1. And are there materials that behave like this? Yes, almost all materials behave like this in the early stages of deformation. So that's a very satisfying model. And again, I'll show you data and so on in the next lecture. Now, another model that is popular is the so-called Gent model. 1 minus 3 over Jm. Sorry, I'm flying through this now. I'm 2 minutes late. I'll finish under the hour. All right. It is like this. Now there's a log. That's weird. And there are two constants, mu0 and Jm. And what are the values? Just like earlier, what are the values of mu0? What are the values of C1 and C2? These are values you find from the data, right? You do some experiment. You say, I think that this is a Mooney-Rivlin material. So you collect the data, and then you say, oh, well, I can see that the data fits when C1 is 3 and C2 is 5, or something like this. I'll show you again in the next lecture. In that case, you will find, so I need to differentiate. I will only have this derivative here. The second one is going to be 0 because there's no dependence on I2. I will find minus PI plus mu0. The Jm is going to disappear. The 2 is going to disappear. And then I'm going to have 1 minus, that's what the log is going to give me. once I differentiate it. And that's not pretty, so I'm just going to multiply top and bottom by Jm plus 3 minus R1p. So that's really interesting. We could see that the stress blows up. We could see there's a singularity here as I1, which is, remember, the sum of the principal stretches squared approaches Jm plus 3. Yeah, if I1 approaches Jm plus 3, then the denominator here is going to tend to 0, and then this quantity is just going to go to infinity. And so it tells you there's a sort of barrier, right? I1 cannot go beyond Jm plus 3. And it suggests to you that the stress is going to increase, and then as it approaches the barrier, it's going to blow up like this. And this is what you observe for many. Oh, I don't have a piece of rubber here, but for many materials, right? If you have a piece of rubber, it's easy to stretch, and then as you stretch more and more, it becomes harder and harder. So low stress in the beginning, and then harder, and then you can't go any further. There is a barrier. There is an asymptote, and that's why this model is excellent to model this what's called this strain stiffening. Very popular, very simple as well. Also popular with the applied mathematicians because again you can make good analytical progress. Okay, I'm nearly there in my list. Then there's something called the Fung material. And it's a material with an exponential growth. If I put again, it depends only on I1, so there's only the pressure-like term, and then there's only a B term. It's going to be mu 0. The B are going to cancel out. So I'm doing those different derivatives very quickly. You can do them again at home if you want. You can see here that as the strain increases, B is going to increase, but I1 is going to increase. And so if I1 increases, you're going to have an exponential growth. So that's popular for good model. I should have written it out. For tissues, soft tissue, biological soft tissues, right? It suggests that in the beginning it's easy to deform, and then there's a gradual and then faster and faster increase in the stress. Very close to the Gent material as well. Okay. And then finally, the final one for today is the Ogden model. Ray Ogden is at Glasgow University. He's a very nice guy. I've written many papers with him. In the 1970s, he proposed this model, and now if you open any software, you will find the Ogden model, like any finite element software. And it's like this, mu n over alpha n. So that's a model where the W is expressed in terms of the stretches. Where n is an integer, that's the so-called order of the model, and mu n, alpha n are constants. They are such that mu n times alpha n is positive. So they're either both positive or both negative. And that gives you the following principal stresses. So if you differentiate Then the alpha n is going to cancel out. You're going to be left with mu n. Oh, not lambda 1, so it's only lambda I. Alpha n to the power lambda I to the power alpha n minus 1, but you have to multiply by lambda I, so you're going to end up with the same degree. This model is very popular with experimentalists. The reason is that you can, n is just an integer, so you can just pick whatever integer you want, and you can just crank up the number of terms in this expression. So if I take n is 3, I will have mu1, alpha 1, mu2, alpha 2, mu3, alpha 3. I will have 6 constants that I can use to adjust my data to the prediction. And so you can get an excellent fit then. And people are happy because they are a good fit. There's problems arising from that, and I will evoke them later. Gee, I'm sorry, I just went over an hour. I guess it was because of the feedback in the beginning. The recording will be 50 minutes, so it should be okay for those of you who are catching up later. I think that's it. I'll stop recording.